Could you see the files? Oh, by mistake I have written 10. Sorry, I'll change that before I upload. Sorry. Welcome to 11th week live session. So let us start. Mainly today's tutorial is based on CG coefficients. Okay. Just a moment. Okay, you can hear me, see me properly. Okay. The matrix element will be non-zero if m1 minus m2 greater than equal to 3. So which option is correct here? So Lx and Ly we can replace in terms of the ladder operators. So L plus minus is Lx plus minus I Ly. This we know. So Lx plus I Ly is nothing but L plus. So that matrix element is this, and what does L plus do? So it will be proportional to up to a proportionality constant that we are not interested right now. So this we will get. So what does it mean? It means for this to be non-zero, m1 has to be equal to m2 plus 1, right? m1 should be equal to m2 plus 1. That means this option is correct. And if m2 equal to m1, then also then this matrix element will be 0, right? If m1 equal to m2, then of course these two states are different and these are all normal orthogonal. So that's why if m1 equal to m2, that matrix element is 0. Fine. Okay. Consider this state. Using this information, answer the next two questions.
Madam, why m1 is equal to m2? Why m1 is equal to m2? It is orthogonal. Can you?
So these are eigenstates of. So eigenstates of. So L square acting on Lm gives h cross square L into L plus 1 Lm. Lz acting on Lm gives Lh cross. Sorry. m h cross Lm. So Lm is what? Lm is nothing but simultaneous eigenstate of and also L square Lz commute. So Lm is nothing but simultaneous eigenstate of L square and Lz. And since these are eigenstates are defined to be orthonormalized. So these are all orthonormalized. Just like in harmonic oscillator state n and state n plus 1, which you get after acting the ladder operator on state n, these are all orthonormalized and that gives 0. In the same way, Lm1 is orthogonal to Lm1 plus 1. So that's why when m1 equal to m2, this matrix element, the given matrix element is 0. Clear?
Yes, ma'am.
Okay. Consider this state vector. Okay. The possible measurements of square of angular momentum operator on the eigenstate 2, minus 1 is what? Just now I told you the eigenvalue of L square on Lm state. Can you tell me what is the eigenvalue then? If L square acts on 2, minus 1 state? So the formula is this.
H square.
Huh?
This is H square. 6.
Can't hear you. Say that again.
Yes, it is 6.
Okay. Because L is 2 here and M is minus 1. So the eigenvalue corresponding to L square . What is the probability of measuring eigenvalue 2h cross square? If you measure L square on this state, what is the probability of measuring 2h cross square? Can you write or unmute yourself and let me know what is the probability of measuring eigenvalue 2h cross square?
Madam, 4.
4?
Yeah, yes.
How did you get that? How did you get 4? Can you just explain the procedure? Yeah.
L is 2.
You are saying
L is 1. L is 1.
okay. So then L plus 1 is 2. So when you are it should be one side L square and L plus 1 whole square. The multiplication 4. what is L into L plus 1 whole square?
That is the problem. That is the expectation. That is the expectation.
How do we calculate the probability? So So given a state psi, okay, you are measuring
Psi into psi star. So psi into psi star equal to 1.
Now you are telling me the orthogonality condition. This is integration dx, sorry, orthonormalize. This is how we do orthonormalization of the state psi. Not orthonormalization, I mean normalization of the state psi. We do this particular way. But I am asking you how would you calculate probability? Probability of measuring eigenvalue, and the eigenvalue is of operator L squared. That is clear from the previous part, since these two parts are related, so L square is not mentioned here, but eigenvalue of L squared, that is 2h cross square. What is the probability? It's not 4. The way, so you have squared the eigenvalue, but that should not be the probability. That is not probability. We have done many problems of finding out probability. Given a state, what would be the probability of getting eigenvalue 2h cross square of operator L square? You have to project, right? The given state, you have to project onto the state for which you are trying to measure the probability. So psi x comma 0 is given to be 1 over square root 10 2 comma minus 1 plus 3 1 comma 1. Okay. Now if you measure L square on this state psi, this which particular state among this linear combination, so in this linear combination, which particular state will give you 2h cross square? This will give you 2h cross square, or this one?
The last one.
Last one will give, because this one you have already checked, this gives 6h cross square. So the question is basically asking you what is the probability that this particular given state, there is a lag I can see on my screen, yeah, so what is the probability that this particular state will collapse into this state, because this state is what gives you 2h cross square eigenvalue. And that probability, first we find out the probability amplitude, that is nothing but inner product of the given state with that state 1 comma 1, and then we mod square that probability amplitude to get the probability. And this is what? This is nothing but 9 by 10, that is 0.9 is the probability. Likewise, probability of measuring eigenvalue 6h cross square would be
It will be 1.
It will be 1.
10 by 10. 1 minute. No, it is 1 by 10. 1.
Yeah, I mean from this probability also you can say that the other probability has to be 0.1, because total probability should be 1. Maybe I can just show. Okay. Two atoms with angular momentum J1 equal to 2 and J2 equal to 1 are coupled and are described by this Hamiltonian. Using this information, answer next 3 questions. The possible values of total angular momentum J will be, so total angular momentum takes values from J1 minus J2 to J1 plus J2. Here J1 is 2, J2 is 1, so J will take value from 1 to 3, which means the possible values of J are 1, 2, 3. Fine. Now if the Hamiltonian acts on Jm state, then the energy eigenvalues corresponding to the possible values of the total angular momentum will be, so Hamiltonian is epsilon J1 dot J2. Now total angular momentum is vector addition of J1 and J2. If I do J square, then we get J1 square plus J2 square plus 2 J1 dot J2. So J1 dot J2 is what? It's J square minus J1 square minus J2 square by 2. So the Hamiltonian acting on Jm state is equal to epsilon J1 dot J2 acting on Jm state. Epsilon J1 dot J2 is nothing but half of J square minus J1 square minus J2 square Jm state. So here you will get h cross square J square, sorry, J into J plus 1 minus J1 into J1 plus 1. The eigenvalue you already know. When L square act on Lm, we get L into L plus 1 h cross square. Same thing is happening here. It's total angular momentum square, so J into J plus 1 and Jm. Okay. So what is the eigenvalue? So eigenvalue is epsilon by 2 h cross square J into J plus 1 minus J1 is 2 and J2 is 1 for this problem. So J1 into J1 plus 1 will give you 6 minus J2 into J2 plus 1 is 2. So that is equal to minus 8. So now the question is asking then the energy eigenvalues corresponding to the possible values of the total angular momentum J. So total angular momentum take values 1, 2 and 3. So you will have 3 corresponding eigenvalues. So for J equal to 1 comma m, and m can take values from minus j to j at the step of 1. So when j equal to 1, m will be minus 1, 0 and 1. So for this state, energy eigenvalue is equal to epsilon by 2 h cross square 2 minus 8 that is 6, so minus 3 epsilon h cross square. For j equal to 2 comma m, E is equal to epsilon by 2 h cross square 6 minus 8, so minus epsilon h cross square. For j equal to 3, E is equal to epsilon by 2 h cross square to epsilon h cross square. Fine.
This possible value is 2, madam.
Huh?
What is the possible value? 2.
No, it is asking you
2.
multiple answers. No, it is asking. Then the energy eigenvalues corresponding to the possible values of total angular momentum. Possible values of total angular momentum are these three: 1, 2, and 3. So, corresponding to 1, your eigenvalue is minus 3 epsilon h cross square. Corresponding to 2, sorry, am I saying correctly? Yeah, minus 3 epsilon h cross square. Corresponding to 2, your eigenvalue is minus 1 epsilon h cross square, and corresponding to 3, it's 2 epsilon h cross square. So all three are correct answer. See, it's asking you enter the integer values in ascending order. Okay. So basically you had to input minus 3, minus 1, 2. Okay. The degeneracy for the highest value of the total angular momentum will be, so for the what is the highest value of the total angular momentum? It came out to be 3, right? Because J1 is 1, J1 is 2, J2 is 1. So highest value was J1 plus J2, and that's 3. And it's asking what is the degeneracy for this total angular momentum. So Jm, when J is 3, it can take how many values when J is 3? M. So M lies between minus 3 to 3 at the step of 1. Alright? So the degeneracy is 2J plus 1. 7. Clear? Is this clear? Okay. The Klebsch-Gordon coefficient, this particular Klebsch-Gordon coefficient will be non-zero if m equal to, can you tell me? What should be m so that this coefficient is non-zero? What is the condition? Condition is m has to be equal to m1 plus m2. So here, what does that mean? Here m1 is equal to G1 plus 1 and m2 is equal to minus j2 minus 2. So m has to be equal to j1 minus j2 minus 1. First of all, you remember what Krebs-Gordon coefficient is, right? Or should I explain?
Madam, can you explain little bit?
Okay. So there were two equivalent bases. So one compatible set of set of operators j square. Okay, let's take j and j1 j2. Fine. So j square jz. All of them commute. So this is one set, and corresponding to this set we j square later. Corresponding to this, we write the we write the state as j1 j2 j m, where j1 is what? So j square j1 square acting on j1 comma m1 give j1 into j1 plus 1 h cross square, as we just explained, as we just used this formula in our previous problem. Likewise, j2 is the eigenvalue corresponding to j2 square, and corresponding to j square the eigenvalue is j, and m is the magnetic one, that is jz acting on j comma m will give you mh cross jm. So this is one basis that we call coupled basis. Because here you don't know what is m1 and m2 explicitly, you only know m, that is a total magnetic quantum number. And another compatible set, by compatible I mean all of them commute with each other. Another, we can take j1 square j1z j2 square j2z. So the corresponding state is j1 j2 m1 m2. Okay, and that is nothing but equivalent to j1 m1 tensor product j2 m2. So there are two particles there are two particles. Corresponding to the first particle, the angular momentum is j1, corresponding to second particle it's j2, and this is the z component of that angular momentum for first particle and second particle, and they are in these states, and their tensor product state can be written in this compact way, and this is called uncoupled basis. Because here we explicitly know what is m1 and m2 for the two particles. Okay. Now z component of the angular momentum is nothing but additive quantum number. So jz is actually j1z plus j2z. Okay, and so these are two bases, two equivalent bases. So we know that one basis can be expressed in terms of the other basis by similarity transformation, and that similarity transformation is nothing but a matrix, and that matrix is nothing but this CG coefficient we call. So let me write down. So suppose this particular basis we want to write in terms of this basis. So how are we going to do that? So this is equal to identity operator acting on the same state and that identity operator we can replace in terms of the completeness relation corresponding to this basis. Sorry. Oh God, what did I do? So identity operator I can replace by the completeness relation corresponding to the uncoupled basis, and that will give J1, J2, M1, M2 on JM state. Now we usually don't write this J1, J2. We can suppress it basically, J1, J2. I mean, it's understood that J1, J2 is there. So this is nothing but that matrix element, CG coefficient. M1, M2, J, M. Okay. So what have we achieved? We have written down this coupled basis as a linear superposition of uncoupled basis. So this is the uncoupled basis. We have written down the coupled basis as a linear superposition of the uncoupled basis. So and how have we done that? Using this Krebs-Gordon coefficients. So these are nothing but CG coefficients. Okay. Now M has to be equal to M1 plus M2 for the CG coefficient to be non-zero. We can show that like this. So Jz, we said that it's additive. So Jz is the z component of the total angular momentum, which is addition of the z component of the first particle, z component of the angular momentum of first particle plus z component of angular momentum of second particle. So what we can do is take the expectation value of, so this operator Jz minus J1z minus J2z with respect to these two states. Okay. So Jz acting on Jm gives M H cross. Likewise J1z acting on M1 give M1. So M1 M2 is what? It's okay. Here it's tensor product state. You remember that it's nothing but J1 M1 tensor J2 M2. Okay. So J1z, when we write J1z, it's understood that it is tensor product with identity corresponding to the second particle. So this J1z will act on this particular state and will give you M1 H cross. So this matrix element is basically M when Jz acts on this. When J1z acts on this, it's minus M1 H cross, I'm taking common. Likewise when J2z acts on this, it gives minus M2 H cross. So and then what remains is the CG coefficient M1 M2 Jm. Okay, now you see that this is actually equal to 0. Why? Because this is 0. Jz is J1z plus J2z. So this is actually 0. What does that mean? For this to be non-zero, for this Cg coefficient to be not equal to 0, this has to be 0. This has to be 0. Then only this entire thing will vanish, become 0. That's why m equal to m1 plus m2 for this Cg coefficient to be non-zero.
Madam, can you repeat this one again?
I'm saying that this implies, let me not put implies. So basically this is equal to this, and okay, let me write it this way. This is equal to 0 implies, okay, now I'm saying that Jz equal to J1z plus J2z. So this matrix element is actually 0, and when we act these operators on the states, we get this eigenvalue corresponding to this operator, m minus m h cross minus m1 h cross minus m2 h cross, and then this is the Cg coefficient that remains. Okay, and I'm saying that this is equal to 0. So for this Cg coefficient to be not equal to 0, let's say some constant value, let's say 2 or something. So if this is 2, or let's say 3, anything non-zero, then this must be 0, right? This factor has to be 0 for the entire thing to vanish. Entire thing vanishes, but if it is non-zero, this has to be 0. If this is non-zero, this has to be 0. Is this clear? Because the entire thing is 0. So that's why we say that Cg coefficients are non-zero. So the Clebsch-Gordon coefficient, this particular thing, will be non-zero if m equal to m1 plus m2, and that's what we did here. You get what I'm saying?
Yes, madam. Yes.
Which implies m equal to m1 plus m2 for to be non-zero. Oh, that I have written already. Why am I repeating? That implies m equal to m1 plus m2. Fine. The product of the position vector component x, z in terms of spherical rank 2 tensor component will be what? So I've noticed that this spherical tensors were not taught by ma'am during the lectures, but this is something that was taught in the tutorial session. I don't know whether you have gone over tutorials of week 11, have you? Have you seen the tutorials of week 11? I mean the tutorial sessions that are recorded, not the tutorial sheet or the assignment. Yes, no, something?
Please explain, madam.
I'm asking, have you watched the tutorial session that is uploaded there under week 11?
Ye- Yes, madam.
So you must have learned about the spherical tensors, right? So there was one problem, probably the fifth one, where the spherical tensor was being explained. But okay, I will tell you what these are. Okay. So a spherical tensor of rank k actually transforms the same in the same way a spherical harmonic uh, with L equal to k would transform. So algebraically it means
Madam, rank of a matrix means it is what do you mean by rank of matrix? If you can explain a little bit.
it's a tensor. It's like it's like, so spherical harmonic we write as YLM, right? Sorry, YLM, where M can take value from minus L to plus L. In the same way, we define this spherical tensor of rank k, where L is traded off by k and M is traded off by q. So q will take values from, just like M take values from minus L to L. Likewise, q will take value from minus k to k. Okay, and so we know that Lz acting on YLM give MH cross YLM, and L plus minus on YLM give H cross square root of L into L plus 1 minus M into M plus minus 1 Y L M plus minus 1. In the same spirit, this spherical harmonic commutator of Jz with spherical harmonic T give QH cross J plus minus minus okay. Okay, now let's talk about rank 1. So rank 1 means k equal to 1, and a spherical rank 1 spheric Cartesian tensor is nothing but a vector call it V, and so the commutator of Jz, and we know how that commutator holds. It's I h cross epsilon. So commutator of any vector with j I epsilon I h cross epsilon ijk. So let's say you consider your D to be position, so vector to be position vector, and you are considering, let's say, the ith component or the x component, and if you try to find out what is x with, let's say, Lz, then you know it's I h cross epsilon so it's minus I h cross y most probably, but I have to check. But whatever, I meant to say that, so the commutator of a vector with Jz, sorry, not Jz, but for any component of angular momentum is actually I h cross epsilon ijk, kth component of that vector. Let me see if I am writing this commutator correctly. Yeah. So this is known commutator, and from here we can actually try to compute the spherical harmonic. So these are the formulas that spherical harmonic satisfies of rank k, and we want to find out the spherical harmonic in terms of Cartesian tensors, which are nothing but vectors, because that would be useful here, because position vector components we need to write in terms of spherical harmonics. So that's why starting with a vector, we are trying to write down what are the spherical harmonics, and that we will then use to write down position vector component x dot z in terms of spherical harmonics. Okay, so it will be clear. Let me just do this. So this is, I hope, clear. So this is the commutation relation of any vector, ith component of any vector with angular momentum jth component. So let's try to evaluate. So Vx with Jz will be I h cross x z y vy, but this is minus, right? Likewise, Vy with Jz will give you I h cross epsilon yzx vx. Epsilon yzx is plus 1. So it happens cyclic order. In cyclic order, if this order is satisfied, then it's plus 1, otherwise it's minus 1. So yzx satisfying this order, but xzy is in the reverse order, so that's why minus. And vz with jz is equal to 0. Okay. So if we compare this with this, it shows that this must have, if this corresponds to spherical tensor of rank 1, then it must corresponds to q equal to 0. Then only right hand side will be 0, because it gives q h cross times that spherical tensor. If q equal to 0, then only that commutator will be 0. So we can already see that T1 q equal to 0 is nothing but Vz. Okay, so we have expressed spherical tensor of rank 1 with q equal to 0 with the Cartesian component of this vector, z component of the Cartesian component of any z component of the Cartesian tensor or the vector. Cartesian tensor of rank 1 is nothing but a vector. So this is done. Now we also want to figure out what is T1 plus minus 1. So I said no, when k equal to 1, q will take value from minus 1 to plus 1. So minus 1, 0 and plus 1. We have already figured out what is T1 comma 0. Now we want to figure out what is T1 plus minus 1. So we look at this commutator. It shows that commutator of j plus minus with tk comma q gives tk comma q plus minus 1. So that means the tensor actually changes. Okay, I mean the usual way here also. I mean ylm becomes ylm plus minus 1. So let's see what is the commutator of j plus minus with vx. Okay, so j plus
Madam,
minus,
V of Z, Z of Z, Madam, commutation of V of Z and Z of Z,
yeah,
it is 0 for what reason? Can you tell me why, for what reason it is 0?
yeah. So epsilon, whenever two indices coincide, so if it is epsilon z z y, then it becomes 0. That is a property of Lebesgue symbol. It's non-zero only when everything is different, and it becomes 0 whenever any two, at least two coincide, two indices. So Vz Jz is what? I h cross epsilon z z k, but since I and j is same, so it's 0. And then we compared it with this equation that a spherical tensor satisfies, and we said that q has to be 0 for this to be true, and so that means it must coincide, this vector must coincide with spherical tensor of rank 1 with q equal to 0. Okay. Now we want to figure out T1 plus minus 1. That's why we are doing this, so that we can compare with this commutator. Sorry, there is huge lag on my screen. Anyway, so j plus minus with Vz is what? So j plus minus is jx plus minus ijy this is plus minus I jy with Vx and jy with Vx is I minus I h cross epsilon x, y, z, v, z. Okay, so that means plus minus h cross v, z, j plus minus with vx, okay. One more thing before we do that, from this equation we now want to see what is t k0, okay, commutator with j plus minus. So j plus minus with t1 0 when k equal to 1 and q equal to 0 is actually equal to h cross square root of
Madam, Madam, Jx of Vx commutes it's 0, madam.
y. Sorry, oh yeah,
Jx,
yeah, of course, for the similar reason. Minus 0 into 0 plus 1, 0 plus minus 1, okay, times t1 plus minus 1. So this
then
is
it will be minus plus h cross vz, madam.
huh? Sorry?
No, that will be minus plus
Which one?
h cross v. The commutation of j plus minus with vx.
No, because minus I times I will give you plus 1.
Okay.
Yeah, but actually that was not needed. This particular thing was not needed. That's why I'm telling you this. So this relation is commutator of j plus minus with tkq, and that gives tk q plus minus 1, and so this q has to be 0. Q has to be 0. Otherwise it will become either plus 2 or minus 2 if q is anything other than 0. So it means that we need to see what is the commutation relation of j plus minus with vz, because we have already identified t10 with vz, okay, from this commutation. So let's see what is the commutation relation of j plus minus with vz. This is not needed, so I will rub it. So let's see. So this is what the formula gives us. We want to see what this vz will give us. So explicitly, so j plus minus is jx plus minus ijy and these two we have already, no we haven't. So jx with vz will be minus ih cross epsilon zxy vy plus minus I minus ih cross epsilon zyx vx. Okay, so xyz. So this is zxy, so that's plus 1 minus ih cross vy, and then this I and minus I becomes plus 1, and we have zyx, so that becomes minus plus h cross vx. We can take common minus plus h cross and it becomes vx plus minus I vy. Okay, so now we can compare. So j plus minus vz is giving us this, which is nothing but j plus minus t10, and this is equal to square root 2 h cross t1 plus minus 1. So this is equal to square root 2 h cross t1 plus minus 1. Okay, so we can compare these two equations. So this implies t1 plus minus 1 is equal to minus plus 1 over square root 2 vx plus minus I vy. Now this we are going to use. So what we have achieved, let's understand that, because a lot of calculation might make it difficult to understand the bigger picture. So what we have done is, we have written down the spherical tensor of rank 1 in terms of the Cartesian tensor of rank 1. So t10 is nothing but z component of a vector, t1 plus minus 1 is nothing but this particular combination of x component and y component of the vector. Okay, now starting with this we can get all higher tensors. How? Using the ladder operators. So I'll explain to you. So see, in this problem what we need actually, so this problem is given t plus, okay, so this superscript is nothing but rank, and this subscript is what take values from minus k to plus k, so that is m. So here it's written m, I was using q, so m is for spherical harmonic and I am here using q. So just keep in mind that m here is nothing but q in the solution. Fine. So we now know this and this, but we don't know these. Okay, so let me just tell you how to get these. So how will you get, oh, we don't know any of these actually. These are for spherical tensors of rank 2. So far we have shown only spherical tensor of rank 1. So let's get on to it. So a spherical tensor of k equal to 2, q equal to 2 is nothing but tensor product of a spherical tensor, let's call it what will I call it, a spherical tensor, let me use that notation. So k I'm using in the superscript. So spherical tensor of rank 2 with k equal to, with q equal to 2 is nothing but spherical tensor of rank 1 q equal to 1 tensor product spherical tensor rank 1 q equal to 1. So this is true even for, so when we do J1, J2, Jm, we have seen that this can be written as linear superposition of M1, M2, J1, J2, M1, M2, right? And this is nothing but tensor product of J1 M1 with J2 M2. Here the similar kind of thing is happening. So, and one more thing I want to point out, that so this is the coupled basis written in terms of uncoupled basis. When it is the maximum m value, which ma'am called stretched state in the lectures, that is nothing but J1 when M1 equal to J1 tensor J2 when M2 equal to J2. So then only your M will become J. What is J? J here is J1 plus J2. Okay. So that is the maximum state. That is the state for which CG coefficient is 1. I have forgotten to write the CG coefficient here. Okay, sorry. So what I was saying is that, so this happens for the coupled and uncoupled basis, and when M is J, where J is J1 plus J2, the maximum value of J, that for that the CG coefficient is actually 1. So that's why you get only this, with M1 equal to J1 and M2 equal to J2, because M has to be equal to M1 plus M2, right? And the same thing we are doing here. So spherical tensor of rank 2, so 2 you can think of as this J, okay, and Q is like M. So spherical tensor of rank 2 with Q equal to 2 is nothing but spherical tensor of rank 1, where Q has to be the maximum possible value, that is 1. Basically here also Q should be equal to Q1 plus Q2, so that's what is happening. And if it is maximum, then the CG coefficient is 1 for that, because none of the other tensors will give you Q equal to 2. If you think that Q equal to 0 and tensor Q equal to 1, but that will give you Q equal to 1, right? The addition of these two Q. So only these two spherical harmonics, if we take tensor product, that can give us spherical tensor of rank 2 with Q equal to 2. Fine. Now we want to figure out these values. Spherical tensor of rank 2 with Q equal to plus 1. Okay. So this we already know. So let me write down the Cartesian component as well. So Q equal to 2 is equal to T11. And what is T1 plus 1? From here you can read off. That is nothing but minus of 1 over square root 2 Vx plus I Vy. So T Q equal to 2, K equal to 2 is nothing but minus of 1 over square root 2 Vx plus I Vy, okay, times again a spherical tensor of rank 1 with Q equal to 1, that is again minus 1 over square root, same thing, times minus 1 over square root 2 Vx plus I Vy. So this is 1/2 Vx plus I Vy whole square. Okay, since I have changed the notation, let me just write down. TKQ is TKQ. This is what I have changed. Fine. Okay. Now we want to see what is TK. T2 Q equal to 2, which is equal to T1 Q equal to 1 tensor T1 Q equal to 1. So on this on this equation, both sides, we act with the lowering operator, j minus. So j minus, but when j minus acts on uncoupled basis, you know that j minus has to be replaced as j1 minus tensor identity plus identity tensor j2 minus. Same thing we will do here. On the left hand side, it's like coupled basis, so j minus acts on that, but right hand side, it's j minus tensor identity plus identity tensor j minus for the two spherical harmonics. So okay, so let's evaluate the left hand side first. This is h cross square root of k into k plus 1 minus q into q minus 1 t q equal to 2 minus 1. Okay, so that gives square root h cross square root 2 into 3 minus 2, that is 2h cross, basically 2h cross 1. Okay, now RHS will give j minus acting on t1 q equal to 1 tensor q equal to 1 plus tensor j minus acting on, okay, so that will give us, this will actually be square root 2 h cross q equal to 0 plus, again from here you will get square root 2 h cross so I can take 2h cross common. Okay, now so we compare both sides, LHS equal to RHS. If we do, okay, so in terms of, so T2 q equal to 1 is equal to h cross by 2 it will become h cross over square root 2, because 2 is here on the left hand side and right hand side is having square root 2, so h cross over square root 2 Now we can write down the corresponding Cartesian component. So we know what is T1 q equal to 0, it's Vz. We know what is T1 q equal to 1, it's minus 1 over square root 2 Vx plus Ivy, Vx plus Ivy plus again minus 1 over square root 2 Ivy times Vz. So what do we get? We get h cross will also get cancelled from both sides, because left hand side we also had h cross here and h cross here, so they get cancelled when we equate 2. So 1 over square root 2, and so ultimately we get minus Vz Vx plus I Vy. Okay. Likewise, so we now know what is T2 q equal to 1. We can further do the lowering operation on this equation, j minus on both sides, and that will give you T2 q equal to minus 1. Do you want me to do that? Or I mean, you now know the procedure. Do you understand the procedure? It's then I will write down the answer for T2 q equal to minus 1. Otherwise I will repeat. Have you understood what we are doing? So we started with the stretched state, which is this, and then we lowered. We operated by the lowering operator on both sides to figure out what is T2 q equal to plus 1. Now once we have obtained T2 q equal to plus 1, we can lower it further to get T2 q equal to minus 1. So okay, maybe I'll write down the answer. This will come out to be similarly T2 q equal to minus 1 will come out to be, let me see, that will come out to be Vz Vx minus I Vy. Okay, and what is T2 q equal to minus 2? That can only come from this state, spherical tensor with when for both the spherical tensors when q equal to minus 1, that will give us q equal to minus 2, and that is equal to 1 over square root 2 Vx minus I Vy, 1 over square root 2 Vx So now we have all the ingredients that we need to solve this problem. So I have explained all of this, but you may not, you cannot do it during the exam. So if probably they will allow formula sheet, there you can write down the spherical harmonics in terms of Cartesian components, which you can use during your exam. Or if they do not allow formula sheet, then probably they will provide the spherical harmonics. Something like that will happen. Okay, so A option is saying minus I by 2 minus I by 2 T2 plus 2 minus T2 minus 2. Okay, so we have all of it. So that this is what. So okay, now further the problem is saying not for any vector but for position vector. So that means V here is x I cap plus y j cap plus z k cap. Fine. So for us, for our problem, so Vx is nothing but x plus Iy whole square by 2, that is x square minus y square plus 2ixy by 2. Likewise V2 plus 1, which is equal to which is equal to Vz times Vx plus Ivy. So Vz for us is Z, Vx is X plus Iy. T2 minus 1 is plus Vz, that is Z, Vx minus Ivy, and T2 2 is equal to X minus Iy whole square by 2, that is X square minus Y square minus 2Ixy. So if we now do this A option, what do we get? If we subtract these two, we get 2Ixy, right? And that is nothing but xy. But question is asking x dot z, xz. So A option is definitely not correct. Let's add the two. If we add the two, B option is saying plus, and that will give us, if we add these two, we will get x square minus y square. So B is also not correct. C option, minus half T2 plus 1 plus T2 minus 1. So what do we get here? If we add these two, we are going to get minus 2I zy, right? These two will get cancelled if we add those two. So minus 2I yz, so again not xz, so it is again I yz. So D option says minus half t plus 1 minus t minus 1. So t plus is this. This, if you subtract from this, we get xz. So that is xz. So D option is the correct one. Ask me any doubts. I will explain to you. No doubts? Sorry, I think it was very lengthy. Okay, fine. Then let's move on to the next one. So the matrix element of x between, so what is x operator? Again, we need to use the spherical harmonic, spherical tensors. So x, we saw that t1 plus minus 1 is equal to minus plus vx plus minus Ivy over square root 2. So for position element, so we consider the vector to be xi cap plus yj cap plus zk cap. So in that case, it's x plus iy square root 2 x minus iy over square root 2. Okay. So if we subtract the 2, that means if we do this, sorry, the other way around. minus, that will give us square root 2x, or x is basically 1 over square root 2, that spherical tensor. Okay, so the matrix element that is given to us is this. Okay, 4f m equal to 3 x, 4d m equal to 2 is equal to 2 square root 3 a0. So f means, let's call it m2 and call it m1. So L2 equal to 3 for f orbital and L1 equal to 2 for d orbital. So x operator we can replace from here. So 1 over square root 2 t1 minus 1 minus plus 1 So what do we get? So left hand side if we evaluate, L2 equal to 3, M2 equal to 3, I'm doing the first term, that means t when k equal to 1 and q equal to minus 1. Okay, L1 equal to 2, M1 equal to 2. So this is equal to, okay, so let me write down the formula first. L2 M2 spherical tensor with rank k, q, L1 M1, this is actually equal to L2, so it was given in the tutorials, L1 times the Krebs-Gordon coefficient L2 M2 K L1, sorry, M1 M2 or M2 M1, K L1 Q M1. Okay, so okay, that is the formula. But something is wrong, it seems, in the formula. Just a moment. I'll check. Okay, I need to check this formula. Okay, I mean on my copy it's written this, but I feel this should have been m2 m1, but I'll check this and do this problem next time. Fine.
Well, this is the last, I think, class.
Really? No, there is one more tutorial session, that is 12th week. It's 11th week, so 12th week is there. But
Okay.
while writing I didn't notice much, but now I feel a little confused with this formula. But basically the procedure is that we need to figure out the left hand side for this one, and then take ratio of this with this, and that will give us some constant. And since this denominator is given, we can multiply this and find out t. That is the procedure, but right now I'm just getting confused with the formula. Okay, maybe whatever is written, I am doing it. If it is not correct, then I will correct. Then I will modify next time. So the left hand side. So for this left hand side, the first element is this. That will give us. Okay, so this is constant. This do not depend on m1 and m2. Okay. Oh no, everything is fine. So this is like the coupled basis. So this is like Jm, and here it's J1, J2, M1, M2. Okay, this is the uncoupled basis. So this is absolutely the CG coefficient. Okay, so this is the CG coefficient. Fine. So that is the formula. I will box this. Okay, so I am evaluating right now this particular term. That will give us L2, which is 3, some function which is a parameter of k, that is a constant, times that CG coefficient. So 3, 3, let me write down. K equal to 1, L1 equal to 2, Q equal to -1, M1 equal to 2. So you can see this has to be equal to 0. You see why? So although these are written differently, like you are used to see M here, M1 here and M2 here, but don't get confused with notation. It's the coupled basis, it's the uncoupled basis. So basically the magnetic quantum number Q and M1 addition should match with this magnetic quantum number, but that's not happening. So Q is -1, M1 is 2, so that means Q plus M1 is 1, and that is not equal to 3. So that's why this CG coefficient is 0 and you get 0. I hope it's clear. Now if I evaluate this one, this term,
Can you explain once again, madam, why it is 0?
Because M1 is not equal to M1 plus M2. Can you see that? Here, in the language of this problem, M2 is not equal to Q plus M1. You can see that? Do you see that?
Yes, madam. Yes, madam.
Okay, so that's why it's 0. CG coefficient is 0. So okay, now this CG coefficient is 1. So you get that coefficient. So therefore, if we substitute these in equation, let's call it 1, 2, 3. Substituting 2 and 3 in 1, we get 1 over square root 2, and minus will come because of this term. This is 0, we have seen. So we get minus 1 over square root 2, 3 is equal to right hand side is 2 square root 3 is 0. And the term that we need to evaluate is this. So let's see, that is 4f comma m equal to 2, z 4d comma m1 equal to 2, and z is what in terms of spherical tensor. Okay, so it's L2 equal to 3, M2 equal to 2, it's T10, L1 equal to, so T10 was Vz, and for any vector, position vector, that's Z. L1 equal to 2, M1 equal to 2, this is equal to times the CG coefficient k equal to 1, L1 equal to 2, q equal to 0, and m1 equal to 2. And I'm just telling you the value of the CG coefficient is 1 over square root 3. Now we can just take ratio of this with this one. And what do we get? This is 1 over square root 3. This will get cancelled out, right? And this particular term is 2 square root 3 is 0. Let me also write that down. 4f m2 equal to 3, x 4d m1 equal to 2, that is nothing but 1 over square root 2 minus that is the left hand side that we have evaluated. This was 0 and this term gave us this, that only I have written here. So I am using that. So minus 1 over square root 2 3 sorry, everywhere it should be function of k, that is 1. Okay, fine. So this gets cancelled and we are left with minus square root 2 by 3. Okay, then I can take product. I can multiply that and that is what? That is 2 square root 3. So let me not write that down here. We were just evaluating the left hand side. So this is equal to, okay, therefore that is equal to that, and this entire thing is given to be 2 square root 3 a0. So we get minus 2 square root 2 a0. So the answer t is basically 2 square root 2. Fine. Sorry, my screen has frozen. Can you see? Okay. Is this fine? I mean, you redo all of it, all of these, then it will be very clear to you. If you don't do it by your hand, then things may look scary. But these are actually very simple, straightforward. Fine. Okay. So oh, here again I have made a mistake. It should be 10. So many typos. Anyway, okay, so this problem is actually not correct as I saw, because it's an electron, so spin is half and L is given to be 1. So total angular momentum can take value from L minus S to L plus S, which is half less than equal to J less than equal to 3 half. So J can take values 3 half and half. So the question is actually not correct. So I just wanted to point that out. Because it's given J equal to 5 by 2, which is not possible for an electron which is in orbital angular momentum L equal to 1. Okay. So anyway, so I think this 9th and 8th problem was really very lengthy, but you do it by your hand, then things will become clear. And ask me any doubts if you have in the last tutorial session, assignment session. Fine. Let us stop here then, if you have no other doubts. Okay.
Madam, please upload this one today.
Yeah, sure.